Putala. Very good morning to all of you.
Good morning, sir.
Yeah, thank you very much. Yeah. Hope all of you can hear me. Today, I'm in the university and conducting this Zoom session. Hopefully you are at home. Be safe over there.
තාත්තේ අන්න කවුද ඇවිල්ලා කවුද ඇවිල්ලා දන්නවා
Flow and non-flow system means flow systems and non-flow systems. Okay, flow systems and non-flow systems. පුතාලා මේ ගැන මම කියලා දුන්නද කට්ටියට? Did I share this with you? Yes or no? Yeah. Okay. And we will be looking into the examples. Okay, examples. So don't worry. As I mentioned to you, we will learn step by step, right? From known to unknowns. So don't worry. I will start with the known things. Right? Systems. Yeah, so after that, we are going for the energy equations. So don't worry with that. Yeah. Let's say examples. For the examples, I will go to the web and I will look for some pictures. Even I can share with you the searching Google. Let's say example compressions. Centrifugal okay pumps. Yes, you can see the pictures. So I will take one here. I will take one. Maybe which one shall I take? Okay, I will take this one. This is a pump. Okay, so what you can notice is here always there is an inlet and outlet for open systems. Okay, so this is the inlet. in. Okay, in is here. What is, if it's a water pump, of course, what is the inlet? See here. You can see the word inlet as well here. See, suction means, suction side means inlet. See the pressure side, this is the leaving, okay? So this is the leaving side. Better I this and then system means, yeah, later we will see what system. So this flow system, okay, flow system, okay, this is flow system. And if you model this, okay, if you model this, see, I consider this is your pump, okay, this is your pump. Let's see, by right I should not have any, let me format this. Good morning, Miss. Lecture එක කශු කමිස්. This is your pump, okay? System, okay? Pump system. Yeah. Very interesting. Feel good and feel free to understand this better. And you have an inlet here, okay? So your inlet, and mark it here. This is in, okay? Okay, this is and there is an outlet.
Excuse me, sir.
Yeah,
May sir, tamar may centrifugal pump ටික විතරයි පෙන්නන්න අපිට Google එකේ.
sorry.
Internet එක search කරපුවා.
Then hari neda, thank you.
Hari sir.
Yeah.
Hari sir.
Right. And out, okay? Out. 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 Good. And here you can see, Putana, there is a motor behind the pump. Okay, there is a motor behind. Okay, electric motor. Okay, Okay, there is an electric motor behind for sure to drive the pump. So there is a work input. Okay, there is a work input. So this in means flow in. Okay, this in means flow in, and this out means flow out. Okay, the flow means the working fluid. Okay, the flow means the working fluid. Flow in, flow out, and there is a work done. Okay, from the motor here. So this motor turns the impeller here. Okay, even in a small pump, you will see impeller. So motor somehow turns, there is a rotating part. So motor, electric motor, I used the word motor, but we call this motor. Okay, motor. Yeah. Motor, M-O-T-O-R, or even I used to use the word motor. Yeah. Because sometimes when we work overseas, we have to use the others what they are using to work input here. W in. I think okay. I use the same arrow, same standard. W in. Okay, W in. So I just to organize this, maybe I will put flow in here. Okay, flow out here. It's okay, yeah? Yeah. And this is your W in. So your W in is this. Work. Okay, work in. So this is work in means this is the network. And you know, generally, so when the pumping is there, there can be heat generation. Okay, there can be even a minor scale, there can be a heat generation. Okay, there can be heat generation. So heat. So let me put it like this. Heat. Okay, heat. Okay, so work. Yeah, and this is heat. Heat. So that is what we call the system. Okay, so you model this. So this is a model. So this is an actual design. Right side, you will see a model. Okay, so this pump system model. So this is a kind of a physical model or thermodynamics model. You can say like this. Okay, Bhutana? Yeah. So for sure, this is an open system. Okay, this is an open system. Yeah. Quite interesting, and the dash line here, we call it system boundary. Okay.
Excuse me, sir.
Yes, sorry, it's muted. Thank you. Please. පුතා ඕන වෙලාවක අන්නේ වගේ කියන්න ඕනේ. මොකද මට ඇහෙනවා කොහොමද? Yeah. So here now you know this is the system boundary. Outside the boundary we call surrounding. So outside the boundary we call surrounding, and within the boundary we call it system. Okay, within the boundary we call it system. So this is a quite nice model. Okay, this is how we model. Okay, so this is a open system model, or this is a flow system model. Okay, so this is a model. So quite interesting. Okay, so this is the model here. So left side is the design. Okay, left side is the design. So before the design, some theoretical modeling would be important, of course. Here, this is the basic thermodynamic model, because here flow and energy model here. Flow and energy model, or we call this thermodynamics model. Flow, work, and energy. Okay, so this is the model. Flow, work, and energy model. This one. Interesting. So that is only. If you need to really model the next stage, let's say the fluid dynamics model. This is thermodynamics model, fluid dynamics model. We have to really look into the details, okay, of the impellers, of the casings, velocities, and all. That is what we call the fluid dynamics model. Okay, so this is basically the thermodynamics model. Fluid dynamics also is very easy. Don't worry about the names. And combining thermodynamics and fluid, we call it fluid mechanics actually, not fluid dynamics. So combining thermo and fluid, we call thermofluid mechanics. So thermodynamics normally it goes with the fluid. So thermofluid mechanics is the subject you should learn in general. Okay, thermofluid mechanics. If you go to web, if you type thermofluid mechanics, there will be a lot. Okay, and also that is very good. So this is an open system or flow system. Okay, flow system or open system. Good. So let me duplicate this with that. Okay, flow system and open system. So I color the surrounding. Let's say if the surrounding is, I color the surrounding. Okay. Oh, sorry, not that tree. Yeah. Now looks good. So this is the surrounding. Okay, this is the surrounding. So this looks perfect. This looks perfect. So flow in is from the surrounding. It can be a piece of pipe, but that is outside the system. It's from the surrounding. Flow out again to the surrounding. Heat in from the surrounding. Work in from the surrounding. So this is the boundary. Okay. So that's how the system, when you think of the system, it is very important to feel the surrounding as well. Yeah. Otherwise, it is not complete. Yeah. So system means you can think of the surrounding as well. And naturally, the surrounding is considered. If you think of heat transfer, of course. Yeah. So there should be two sides. If one side is the system, the other side is considered the surrounding of the system. Okay. Yeah. So interesting. Okay, and let me look into one more example. So this becomes, how to say, this is a flow system. Okay, this is a flow system. Or even we can call open system. Okay, flow or open. Open system. Okay, non-flow means closed. You can see in your textbooks, text notes, and pass to you, you can see those words. Okay, you can see those words in your textbooks. Okay, but reading alone textbooks, you will not get that much of idea unless you join the class. That's why joining the class is very important for that. Okay, joining the class is very important. Yeah. Oh, sorry. Yes, good. Yes, it's a very nice slide. Okay, now here, the flow system example. Okay, and we will look for one more example. And you can see the, of course, in future you will be learning technologies of everything. Okay, you will be learning the technologies of everything, but of course, step by step. Okay, step by step. The best is, yeah, Sri Lanka, there are pump makers. Yeah, there are pump makers, but motors, electric motor makers, I have no idea. There are pump makers, Sri Lankan brands. Let's see, the water pumps. We have one brand, Solex. Solex water pumps. Solex water pumps. Yeah. Okay, Vita. Yeah, we have one brand. Yes, we have water pumps, but electric motors we are not producing in Sri Lanka. Maybe. So you can see how to you can learn how to make the pumps because you can make it. Yeah, okay, you can make it. So it's manufacturing, of course. You have the capabilities. Think about that. Okay, yeah. And then we will go for another one. Let's say turbine. Okay, or compressors. Let's say we will look into compressors. Compressors. Okay. Now these are air compressors. Okay, these are air compressors. Let me go for a simple one. Okay, let me take this. Just replace on. So here is the compressor. It's like piston cylinder. So you will see in. I believe this is in. I just put like this. In. Okay. And out. There's a common outlet. You can see. This will be the out. Somehow this will be the out. So out goes to the pressurize the storage tank. Okay, so this is the out. Okay, so you have in and out as well. So again, this is a different case, but you can see there is an in and out. Okay, there's an in and out. So there should be flow in, there should be flow out. There should be work in, there can be heat interaction. That's why this has some fins on this head of this piston cylinder mechanism. You can see. Again,
excuse me sir අපිට මේ presentation එක පේන්නේ නැහැ.
sorry.
Google එකේ search කරලා පේන්නේ තාම.
Sorry, thank you for reminding. So this is the one. So you can see, yeah, in and out. In means this is the suction, goes to the compression mechanism, and then of course here two heads. You can see two-stage compression. This one. Later you can learn about this. So one stage, two stage after compression, pass it to the storage tank. Okay, compressor storage tank. So for the system here, in and out, you can see same like the right one. Okay, another example. Okay, now I will go for refrigerant compression. Okay, this is air compression, this one. First one is water pump. Okay, first one is, this is a water pump system. This is an air compression system. Okay, and let me look into refrigerant compressors. Okay. We are spending little time, but we need this time, we need this time. Let's say refrigerant compressors. So air compressors, working fluid is air. Okay. Refrigerant compressors, you can see different types. Refrigeration is a very important field, belongs to the field of thermodynamics. Okay. In your house, refrigerators, if you have, you can see this kind of smaller ones. These are high-tech, some linear compressors, it seems. We'll see. And we have the compressors like this. Inside there are piston cylinder system like here. Okay, like here. So let me take this as an example. Let me take this. More challenging one. Okay. Yes. Okay. This is the one. Big enough? Okay. Big enough, huh? Big enough. Good. Ah. Yes, now you can see. So here this is a design. This is actually product. So here you can see the pipe. This is the inlet. Okay. Yeah, that's the inlet. And this is the outlet. See, copper piping here. Somehow you can see goes here and common. So this is outlet. The other one can be the service pipe. Okay, this one can be a service pipe. So you can see in and out again. So you can see here. So in the previous one, it's not the pump, it's an air compressor system. So this one is the refrigerant compression system. You can see in and out. So when you model this, it's like this. Again, you can see here. Work done. You can see the electric motor here. Okay, somewhere you will see this. Electric motor is there. And of course, that is inside, but system means the piston cylinder is here somewhere. See, you can see somewhere here maybe. So work in is there because of the electric motor. Heat, you can see this compressor is hot when this runs. Okay, and even this leaving side, refrigerant is quite hot that even you cannot touch the pipes. Okay, so which means the heat interaction is there as well. Okay, yeah. So that's how it is. And this shaft, this is the rotor shaft, and oil is seen. So some lubrication is taken place. Some lubrication is taken place. These are very nice, very precise machine designs. Very precise machine designs. So, this is with some. This is a Danfoss brand. See Danfoss. See, this is with some controllers. So some frequency controllers, PLCs, to control the speed with the cooling load. Okay, so what you can see is all a high tech. Okay. Good. So I have one question not related to thermodynamics, but let's see. Air compressors we can produce here. We have certain market. Okay, we have certain market we can produce, but still to have varieties of products, our market may not be that big enough, local market, unless we have exports. Okay, the same way, refrigerant compressors. So you have to have at least few millions of units production to sustain this compression making. Few millions of unit production at least. That's why you can see these compressor makers are generally focusing on big markets. If not, it is not possible to sustain as an industry. Okay, you can see compressors made in China, made in Korea.
Hello, sir.
Yeah, Buddha.
මට ප්‍රශ්නයක් තියෙනවා සර් ටෙස්ලා වෙහිකල් එකේ ආයිලට් සිස්ටම් එක ගැන පොඩ්ඩක් කරන්න පුළුවන්ද?
හරි පුතා ඒක ඊට පස්සේ කතා කරමු ඊට පස්සේ කතා කරමු. හරි. මේ ටෙස්ලා වෙහිකල් එක ගැන මාත් එච්චර දන්නේ වාගෙම දැනගෙන තමයි ඒක දන්න වෙන්නේ. So we will look into that. Very good. බලන්නකො ළමයි හිතන හැටි. Excellent. So here Putala can see now this is you don't have even made in India. Yeah, there are made in India compressors also. But small countries, they cannot have this kind of manufacturing because sorry, so that's how if you think of the economics of manufacturing this, always you have to have a volume for production. That's why, so as students, this learning of economics, manufacturing related to technology and all very good, because uh, you may feel challenged to start this kind of industries in Sri Lanka because the market issue. Okay, because the market issue and the investment for this are in hundreds of millions, if I'm not mistaken, hundreds of millions. And your network, your system of in the manufacturing system, starting from logistics to marketing and after sales, and dealing with the manufacturers of the refrigerators and all, this is a huge task. It's a huge task. That's why making a compressor is not just making it. Yeah. So you have to produce in millions, and you have to have the perfect quality with no quality issues, because if the quality issues are there are problems for the manufacturers. Example, let's say this costs $100 and your refrigerator costs $500. Because of this $100 piece, if there is a problem, it's a question for the $500 unit. That's why. So you have to be very responsible when you produce parts for the others to manufacture. And also, if you start manufacturing something, it is very important for you to outsource very reliable parts. That is very important. So manufacturing is something, it is more than technology. So one day you should be manufacturers. Keep this dream, not about making the compressors, but you can think of producing many, yeah, to suit for our economies. Yeah, even you can start exporting also. That's why you have to be very smart on identifying what are the products you can produce. You have to think of your market, availability of raw materials, and your systems of operations and all. And this is the time for you to think. මම ඒකයි පුතාලා මේ ටික කියන්නේ මේවත් අපි දැනගන්න ඕනේ නිකම්ම මේ පොතේ තියෙන ටිකක් විතරක් දැනගෙන බෑ. And also about the compressors. Yeah. Do you think the best compressor has already been invented, the best compressor? No, the best compressor is yet to come. Maybe a very simple solution. And you may be the one inventing the best compressor. You may be the one inventing the best compressor. So you have to have that motive, that vision, that goal. That is very important, because learning only this as a text just to pass the exam is not a big deal. Now, once you feel the interest, you can pass the exam, no issues at all. But to become somebody to contribute, yeah, you should be exceptional. So everyone is exceptional, but that is hiding within you. So you have to think how to wake up your true potential sleeping within you. That is very important. That is very important. So that gives some meaning for even these lessons, Putana. Yeah, that is very important. Yeah, good. So this is about open systems. So I will look into just one more only for your interest. I will look into just one more. So later you can explore really. So I will look into just one more from the power side. Okay, power side. Let's say steam power plant, steam turbine. There are engines as well, steam turbines. In Norachole and North Sea, the massiveness. I think we have seen this. If I'm not mistaken, we have seen this. Steam turbines. We have seen this. Yeah. So when you look at this, you have to look further. You should see what you cannot see. Yeah, that is very important. You should see what you cannot see. Yeah, that is very important. So I'm looking for in and out here. Again, steam turbines. Yeah, in and outs. Let's see. See the massiveness. See the massiveness. Yeah. Huge ones. Even we can try doing the smaller ones, some smarter ways. Yeah, why not? Yeah, for simple applications. Yeah. So looking at the big things, never think that you cannot do. Okay, you can do at smaller scale. Yeah, that's how we should think. And this may not be the best, the best is yet to come. That's how we should keep the options open for our innovations. Yeah. Yeah. These are massive. By the way, these are massive and very reliable. You can see. Yeah. Yeah. Let me take this. So I'm replacing this. Okay. That's why flow modeling is the same. You can see the inlet. Here is the inlet. You have noticed the outlet here. See the outlet this way. Outlet. And then this one, work done. Okay, this one, work done on the generator. So this delivered the work. Okay, this delivered the work. So that one is if I put another arrow, let's say this is your W. Okay, this is your W. Work done. Work done. This is the generator, and here you can see even there's a heat loss. Heat loss. Can you remember the compressor problem we have analyzed? Yeah, we didn't do the final one. There it is asking the heat loss or something. I can't remember the question. Heat loss. It is something like this. So left side is your design and also the construction based on the designs. Right side you can see the model. In, flow in, flow out. So this case work out means work in is negative. Okay, so it's only the sign. So this is negative work in. Okay, work done means negative, work in is negative because work out is there. Heat in, here heat loss means this is a negative heat. Okay, and of course energy flows with the steam, flow in, okay, flow in with energy, okay, flow out with lesser energy, okay. Yeah, I think enough examples for open systems, okay. And very important point, one more here. For a proper operation of this flow should be steady.
Excuse me, sir. My presentation is paying now.
Thank you, Vita. Thank you for reminding. Yeah, thank you for reminding. Yeah. Oh. Yeah. So this is what I have done really. This here, the turbine, you can see the in, steam out. Now the work done is here, W, but here work out, work not work in. So network is out, means it's only the sign, work done. If we consider minus means work in. And that one we will discuss later. And the heat loss, of course there is a heat loss. Yeah. So that's why, again, heat interaction. So you can see the left side and right side. There is a match. So you know that this modeling is reasonable. Okay, this modeling is reasonable. And this is the steam turbine system. So instead of refrigerant, I would say steam turbine system. Okay, good. So so you can think of how to make the smaller ones. Yeah, because as I mentioned to you, the best one is yet to invent. Maybe you are the one. Yeah. Maybe you are the one inventing the best one. Okay. So later you can see details of here. How from the steam, the high energy loaded steam, how that working fluid steam can deliver a good work. Yeah. Because the turbines also efficiency are not 100%. It's around, yeah, we will see efficiency of the turbines. Yeah. Steam turbine efficiencies. Efficiencies. Of course, those are the analysis. Those are the analysis. For the analysis, you have to look into the thermofluid. Steam turbine. So bigger ones have high efficiency. They reach top value up to about 50%. The efficiency. So this is practical thermal efficiency of a system. Means the thermal energy out of 100 up to what level is delivered as work. That is 50. 50% is the maximum. Where is the turbine size? Load condition. And the gap losses means some steam without doing any work just bypass. Yeah, because there are clearances. Okay. And also friction losses. I think you are familiar with this now. So they reach top values up to about 50% in 1200 megawatt turbines. In Noracholi power plant, we have 300 megawatt turbines. How many turbines? How many modules? We have 300 times 3 or 4. So around 1200 megawatts. Yeah. So this is talking about that big turbine. So ours, we have 300 megawatt plants. And Noracholi capacities we can see here. So these are huge ones. Yeah. So huge ones have at least a better efficiency, that is 50%. Smaller ones, lower efficiency. Okay. This is in Wikipedia anyway, that is okay, you can see. Turbine efficiencies, some says isentropic efficiencies. You can see anyway, there are rooms for improvements. Okay. Rated thermal efficiencies you can see is around 44.7% and all. Yeah, you can see efficiencies. So for the power plants, they are going for the big turbines. But even for steam turbines can be used for other purposes as well, the smaller steam turbines maybe. Yeah. So Noracholi capacity, Noracholi, let's say Noracholi. Noracholi power plant. Capacity. See, 1200 megawatt, 300 times 4. 300 megawatt coal-fired power plant. Eventually bringing the capacity to this. So now maybe only we have 2 or 3 units. So finally there will be the full capacities, 4 of 300 megawatts becomes 1200 megawatt. So if you build 1200 single turbine, if you install, we have the energy supply also 1200 megawatt, and the efficiency is very high. Let's say 1201, 50% efficient, 301 maybe around below 45% maybe. So 5% energy loss is there because of using the smaller ones. But smaller turbines you can manage. Right. Okay. Smaller turbines you will manage well. So you can see 3 times 300 megawatts currently. Okay. And the construction cost, should be the Noracholi one. Yeah, is 1.3 billion construction cost. See the energy sector and the technology. When you are learning, these technologies are important for the national interest and nationally important ones. So it is very important to learn from the very basics. Basic is not about the words, but underneath the words there are true technologies. The nature works. Yeah. So the steam turbine is some adaptation of nature's things. Okay, so you have the right to understand the steam turbines to fullest, even without words and equations. For that you need a real technological wisdom. There are people. Yeah. So that's why don't worry, you have the potential. You should keep this dream. You should keep this dream, because if you are learning, you have to learn to the fullest. Otherwise, you should not learn. You can do something else. Yeah, very good. So this is about open systems. Open systems. Yeah, open systems. This is about open systems. And then I need to mention that for a smooth operation, the flow should be steady. The flow should be steady. Steady flow is important. Steady flow is important, because if the flow is not steady, there are issues. Okay, there are issues. Steady flow is important. Yeah, steady flow. So even here, the steady supply is important. Yeah, steady flow. But here you can see compressors. Let me take this out. Not for this, but for this refrigerant compressors, again running in the cyclic operations, steady flows important. Steady flow is very, very important. Yeah? Steady flow. Yeah. Because if the flow is unsteady, you cannot have a very good system. Very good long-lasting system is difficult to achieve if you don't have a steady flow. Okay, so the steady flowness is very important. Okay, even here the steady flowness is important, but unsteady situations also you have to analyze. Example like when you commission or when you shut down, so there should be ways of shutting down. There should be ways of restarting this. Even Noracholi to start, it took I think few days, not just one day. So the steady flow is important for the smoother operations, and even for our analysis, steady flow is important. Okay, so steady flow. Okay, steady flow is important. So steady flow means, okay, steady flow means what? Steady flow means what? Steady is a word, but can you feel it better? Steady flow. Can you feel the word better? Practically. Yeah. So we can say flow in is equal to flow out. Okay, so that is the steady flow. Are you satisfied with this? Do you feel that you have to think further on this? Yes. Yeah. Are you satisfied with this? Just to get this information as a knowledge of how you can feel this steady flow, that's why. So flow in equals flow out. Yeah. So to further, I would say mass. The quantity of matter flow in is quantity of matter flow out, mass. Because flow is something matter, or mass in equals out. So in equals out is important, because if not, within the system there is a mass. The system mass vary. When the system mass vary, there can be issues. Okay. Then this is the steady flow condition. You can imagine Imagine a big steam turbine running. Mass flow in is mass flow out. Anything short, mass flow in. If short, mass flow out, we have issues maybe. Okay. Mass flow out less, mass flow in more. There can be some other issues like pressurizing and the operational and even the safety issues maybe. So the in and out has certain balances. Okay, it's a balance. Yeah. So this flow balance should be there. Okay. So we call this flow balance. More practical word, flow balance. Flow is balance. In is what in is out. Whenever something in, the same should go out. Otherwise, there is no chance to go in for the flow. Then there should be issues. Flow balance is this balance. Very interesting. Yeah. Steady flow. Yeah. So in our case, so when we are going to analyze, we will be looking into this steady flow. Okay, mass flow out means this is flow balance. Flow balance, yeah, flow balance. This is a nice word, flow balance. Yeah. So now you have enough examples, and the balanced flow, steady flow, we will be analyzing. Okay. Yeah. Steady flow. Very nice. So let me think in the other way. Okay. So I have to take this out. Let's do this. Let's say no flow in. No flow in. Interesting. Eh? No. Then, of course, there should be no flow out. There should be no flow out. What flow? Mass flow. Okay. No mass flow in. No mass flow out. So mass flow. Flow කියන්නේ පුතා ගලනවා කියන එකයි. තේරෙන්නේ. That's flow. Okay. Liquid and gas, we call both fluids. So we consider that matter flow, flowability. Can you remember? Flowability. Okay, flow. No mass flow in, no mass flow out. Okay, which means බැංකුවල හිමත් ඥාන තියෙන සමහර ඔෆිස් වල closed කියන්නේ no in. තේරුණා නේද? Closed means no in. Of course, with no in, there should be no out. Because otherwise there is no balance. Okay. So now, not about the open systems, but non-flow closed systems. So no mass flow in, no mass flow out. It's a kind of balance again. A balance. Again, it's a balance. Mass flow balancing in a different way. No flow. That's it. Okay. No flow. It's a mass flow balance. Kind of mass flow balance. No flow. Earlier one you have flow, but here no flow. No mass flow balance. Now let's say we have issues. We have issues. Example here. I open this. If no flow, no, this is the symbol. If no flow, okay, if no flow, technically, no outflow as well. Then what happens for this case? In an open system, when there is no flow, no function. For open systems, no flow, no function. Because no work done then. No work done. Also, no heat loss. This is a dead system, or sleeping system. Yeah. So, in that case, this is not about the balance, but this is situation. Okay, this is not operating. Okay, this is not operating. Yeah. But there can be systems. So this is like a dead name. And this is like a dead system. There are no steam in, no steam out, no work done, no heat loss. This is like dead. This is not life. Not to say dead, but this is not life. This is not came into life. Okay. So anytime this can be live when the mass goes in and comes out. So this is not live. Okay. Not live. Not live. No? Close to the working fluid. So working fluid comes from outside and pass through and goes out. Okay. So then this is the situation for this case. No heat, no flow in, no flow out, no work in. So this is something like, how to say? So for open system, so this is like not live or not live. Well, this is not live. So I will take this out here. This is for flow open systems, but there are closed systems no mass in and out, but very much life. There are systems. Okay, let's see. Now I'm going to look into, you know this situation. Yeah? You know this situation. So very nice practical aspects. For open systems, there should be a flow. Okay, there should be a flow. Okay, let's say we will get closed system. Example. Are there live closed systems? Are there live closed systems? Yeah. Open system, when closed, it's not live. Means no flow in, no flow out. Okay. Let's say example kettle. Kettle. No. Let's say this way. Not to say kettle. Let's say this is an open system. This is a different open system. This is a different. You can see complicated. So no in but only out. You can see heating. The boiling is something like a work done here, but some portion of mass go out. Yeah, no in. This is a pressure cooker. So until certain stage, till it builds the pressure to the limit, this is a closed system, pressure cooker. Okay. So these are some workable systems. You can see these are hard to say open systems because no in. Hard to say closed systems because there are outlets. So these are different systems. Sorry, okay. So these are different ones. Yeah. So we have to understand sometimes the deviation from the steady flow. Yeah. This is a deviation. So here net heat in here. So you have some out, but here the issue is you can see this. Yeah, let me discuss it afterward. Here in this case, you have out and no in here, but continuous. Of course, in a continuous operation, sometimes we can see in and out. Even some boilers, the simple ones, you can see in and out, but here no in and out. no in. So heat gas, no in, out. Work done. There is a little work done. Okay? There can be a little work done. So I just put here. Okay. Here's some systems for thoughts.
සර් ප්‍රසන්ටේෂන් එක පේන්නේ නැහැ අප.
Sorry. So these are some systems, of course, thermodynamic systems for thoughts. Yeah, so this is hard to say. This is surely this is not steady flow system, and also this is not closed system. Okay, and this is live. Okay, no mass flow in actually. Not to say in, but initially you pour here. Yeah, so this is a batch wise. Okay, this is a batch operation. So this is not continuous. Work in is no, but hard to say because boiling can be a work. Heat is there. Mass flow out, you cannot say no. There can be evaporations. Yeah. So, and no mass flow in because initially there is inlet. So this is a live but batch-wise operation. This one live and it's a batch operation. In is there, but one time you put this water inside. Okay, and here the purpose is not to have outlet but to have boiled water. Okay, so this is not important. Leaving is not the point of interest. Okay, but the work done is important. Boiling can be a kind of work done. Okay, it is there. So live system, some systems for water, live and batch operations. This is operating as a batch. One time you put in here, almost no out, little out, work done is there, heat is applied. Yeah, so this is not an open system. Okay, this is not open system. And also this is not a closed system. But we should be able to analyze this. So this is a system. Okay, but this is a system. You can imagine some boundaries. Yeah. So this is a system. Yeah. Okay, don't worry about this. Don't worry. If you think of boilers, industrial boilers, industrial boilers. I'm looking for a simple one. Okay, we should look into this as well. Boilers, industrial boilers. In is here. As I see, there should be out somewhere. Let me put out somewhere. Let me put out somewhere. We have to really recognize the place in which, okay. And now you can see heat. See the huge flame, okay. Heat in is here, okay. And then this is how you get the, and of course there is little heat loss also. Even though boiler the heat loss is limited, there can be little heat loss as well. Little heat loss, okay. Little heat loss is possible. And the water in, steam out. So you have flow in and flow out. Okay, flow in, flow out. So again, this should be a steady flow. Okay, this is an industrial boiler, not for power generations, but for the thermal applications. Thermal applications. Work done is how to say this one. Yeah, I take this as out. Okay, so this is again the steady flow system. Yeah, very good. To make it complete. So this is the situation when the flow stops of the steady flow. Yeah. The system becomes not live. So this is a complicated one. This is live and batch operation. During the operation, no in, but there is an out. During the operation, no in, but there is an out. Yeah. So work done, sometimes the lid, you can see jumping and we have some noises and all. There can be. Okay, the heat is there for sure. Net heat, so there can be heat losses as well. So net heat is there. Yeah. So don't worry about this complicated systems. Later we will start. Okay, we will start. So this is not our interest at this time. This may not. Sometimes maybe. So our interest is this one. Okay. Open systems with steady flow. Okay. Steady flow open systems. That is our interest. Steady flow open system is our interest. Steady flow open system is our interest. Okay, steady flow open systems. So here in this case, steady flow, there is a flow balance. Okay, and life and continuous operation. Continuous operation, not the batch wise. So this is live and continuous operation. And if you need an example, this is one example. Okay, this is one example. Okay, live and continuous operation. This is the situation. Right? Continuous operating works. We are going to study. Okay, this is the one we are going to study. Okay, steady flow open systems. What we are going to study is the flow, work, and energy model. So flow, work, and energy model we are going to study. So the flow, work, and energy model. This is what we are going to start here. Yeah, very good. Flow, work, and energy model. So steady flow. Very nice. So model 4 steady flow. Okay. This one. So when you learn this, the outcome is, of course, for live and continuous operation. When you model this, okay, let's see how the model would be. Let's see how the model would be. It's very nice. Okay. Let's see how the model would be. Okay. Energy, work, and flow model. Something like this. Yeah, something like this. So we are going to model it now. So, okay, steady flow. So let's say now steady flow. Steady flow energy model. Flow, work, and energy model. Yeah. Yeah. So be quite patient with that. Right? Yeah. So this is the condition. So flow, work, and energy model. Flow. Steady flow. Okay. Very simple. Flow is steady flow means mass flow in is mass flow out. See how simple? So this is the steady flow. Yeah. So this is mass flow. So steady mass flow. Further. Okay. Mass flow in is mass flow out. And this is really the mass flow balance. Okay. So you cannot, you no need to keep memory on this, but you may have a very good understanding, very solid understanding. So this is the mass flow balance. Okay. I believe you can understand this, Putana. Then comes the very interesting one, balance. Work and energy. Yes, then that one. Okay. So work and energy. Okay. Work and energy model. So all goes together. Work and energy. Quite interesting. Work and energy. Let's say what you're talking again. A balance. Balance. Nothing else. Okay. How you are balancing this. Okay, let's say energy in. We have terms. We will look into the terms now. There should be energy flow with the flow in. Okay. Because flow always contains energy. So that is how the mass, you can see energy aspects in mass. Okay. So energy in should be there. Same way should be out. Okay. Energy in should be there. Energy out should be there. Okay. What else? Heat. Heat. So heat I will use Q. Q in. Q is for heat. Heat in. I will put as Q in. Okay. Q in. You can say this Q in. Q in. Q in. Okay. And E in is together with mass flow in. See E in. Okay. So not no mass flow in, but yes, there is a mass flow. Okay. And there is an E out together with mass flow out. Okay. There is an E out. Together with mass flow in, there is an energy flow in. E. Okay. Together with mass flow in, there is an energy flow in. Okay. Together with mass flow out, mass flow out contains energy. Okay. energy. That is E out. Heat in is here and work in also there. Work in, we use the word dumping. Okay. Now you feel quite good. Yeah. So leisurely but thoughtfully focus on this. One-time learning. One-time learning, nothing to memorize. And finally, nothing to learn also. Right? Finally, nothing to learn. I put this turbine for the memory. So, system boundaries here. Yeah. Okay. So, what are the other things? Work and energy balance. Energy in, energy out, heat in, heat out. Also, okay, also, there can be energy in the system as well. So, energy in the system, let's say E system. E system. System. E system. System energy is E system. Okay. And there is another parameter that you should not forget. Time. Okay, time. So here, period of time shall we take as a time period? Time period. Okay, let's see time. Okay, time. Or even period of time, we can say we use small t for time. Okay, delta t, a time period or time difference. Time taken or time difference. Let's say time, let's say t and delta t, both terms I just put here. Okay, both terms I put here. Okay, mass flow in, M in. Okay, let's say M in. You can have simple level. Okay, mass flow out, you can have M out. Okay, so M in, I will put here M in. M out, mass flow out, M out. Okay, good. So now we are getting more familiarized. Yeah, good. So these are the parameters. Okay, these are the parameters, and we are about to write some expressions for this live, and instead of continuous, I will use steady, better, yeah, live and steady operation. Flow, work, and energy model. Okay, mass flow, steady mass flow, or mass flow balance. Okay, steady mass flow or mass flow balance. Mass flow in equals mass flow out. Work and energy balance. Now we have to write. Okay, so M in is M out. So
Sir, excuse me. Sir, okay, in එකයි out එකයි සමාන නෑ නේද?
නෑ පුතා නෑ සමාන නෑ. සමාන නෑ. ඔව්.
ඒතකොට sir, okay, දැන් ඇතුල් වෙද්දි තියෙනවනේ මේ පීඩනයක්, ඒ කියන්නේ A ගුණ කිරීම V.
ඔව්.
ඒකයි පිට වෙද්දි A ගුණ කිරීම V එකයි සමාන වෙන්න ඕනේ නැද්ද? ස්ටඩි ෆ්ලෝ එකක් වෙන්න.
පුතා ඒ ටිකත් කතා කරමු. ඔව්. කතා කරමු. AV රෝ තමයි පුතා සමාන වෙන්න ඕනේ. Incompressible නම් A වැඩි කිරීම V හරිය. නේද? density එක වෙනස් වෙන්නත් පුළුවන්. හරිනේ? ඔව්. Incompressible නම් A times V කියන එක හරිය. flow rate එක. අපි ඒක කතා කරමු. Right. Even for system there can be mass. M system. I'll put that as capital M. Okay. Okay, good. Mass flow balance is okay. M in equals M out. Okay. That is the mass flow balance equation. Okay. M in equals M out. Okay. Right. So this is the mass flow balance equation. Not to say equation, but that's how the steady flow. Now if we look into the balance of work and energy, if we combine together, we are about to write an expression. Okay, let's say we need to consider timing. Okay, given period of time. Okay, because flow in, it has a certain timing. Okay, period of timing. Let's say timing. Let's say timing. Time of I use delta t. That is okay. That is okay. It's like starting now 10 minutes, delta t means 10 minutes. Okay. It's a difference. Okay. Difference. Or even, let's say, I will put, okay, 10 seconds for your convenience. Later I will change. Okay. At given time of, let's say 10 seconds. I don't mind. Yeah. There is a flow in E in, there is a flow. Okay, and means the flow together with energy together flow with mass in. Okay, and work also, once work is done on this working fluid. Okay, this work is done on working fluid. Because of this W work, energy level of the fluid increase. Okay, Bhutana? Work done on working fluid. Okay. So W in means it's on working fluid. W in on the working fluid. Okay. Heat in on the working fluid. Because all are performing. Okay. All are performing on the working fluid. On the working fluid. Then it's more meaningful, right? On the working fluid. Yeah. So let's say heat in as well. We call it Q in. Q in. So these are the ins. Okay. And be very thoughtful. Because I'm typing on behalf of you. You have to just see and have some understanding. Minus out. Okay, for 10 seconds. E out. Okay. Out is only with this. W means actually W net. There can be some in, some out. So we can say everything together in, this is net. actually net in. Okay, in the net value. There can be out also, in minus out. It is net. In net value. Okay. So these are the ins and outs. Okay, very interesting. W in, I just put the word net because some cases, let's say example, I will take this as boiler. See, huge fire, heat in, and there is a heat loss because this is so hot. There can be heat loss to the surrounding. So heat in minus heat loss is heat net. Okay, yeah, if I write it something like this, heat in minus heat loss, that is net heat in that is Q in net. Okay, that is what we call Q in net. Okay, the best example is the boiler. There you can see it. Yeah, so you can see it here. Okay, Q in net. Same way, in some cases, there can be W net as well. That's why Q in net, W in net, okay, and E out. So let me duplicate this slide. And for this step, I take net out because even though net is there or not, that is net. Okay, that is net. So I can take this net word out. Okay, understand? E out. Okay, so E out, it's only one term. So I take the bracket out. Okay, is equal to what? Now for 10 seconds, certain energy into the system, certain work done on the system, certain heat into the system. And with the flow out, there is a certain energy leave from the system. So any balance is what E system. Okay, the system, I know that you have an issue here. E system, I have to bring this delta here because it should be the delta E or rise of the system energy. Okay, rise of the system energy at given time of 10 seconds. Okay, given time of 10 seconds. Okay, good. So Then you have an issue here, not to say issue, for steady operations. Okay, for steady operations, this is 0. Delta E system is 0 for steady operations. No increase of the internal, the system's energy has no increase. Otherwise, if energy build up, the system can even be explored. That's one. So for live and steady operation, I would say delta E system, okay, delta E system, and delta M system, okay, delta E system and delta M systems are 0. Okay, that is very important because no increasing of the mass in the system. Then it is, if there is an increase, it's an issue. Okay, it's an issue. So that is the point here. Rearranging the texts. Okay. So live and steady operation. Okay. And even operations means you can change, you can take the word out live. Okay, so this is quite interesting. So delta E system is 0. See, is 0. Same way, for 10 seconds, you can write, let's have to make this bit smaller. Same way you can write even for the mass. M in minus M out is delta M system equals 0. It's more better. Okay, it's much more better. Okay, it's much more better. Much more better. Okay, so you can see here bottom two equations. So that two equations plus the right side figure we call the model of flow, work and energy for steady flow open system. Open systems. It's quite nice, eh? Quite nice. So let me duplicate this. Yeah. Slide. So steady mass flow balance. I will put this one. M in minus M out del time system equals 0. That is M in equals M out. Okay. At given 10 seconds. At given time period of 10 seconds. Work and energy balance. You have the key. So so this one becomes 0, so that I take delta I system here. So this is how this in plus W in plus Q in minus out. So two expressions. One mass balance. Or let's say this is mass balance. Mass balance. And this one we will call energy balance. Energy balance. Energy balance. So mass balance and energy balance. The work and energy balance is there. Okay. Don't worry. I will take this out. So work and energy balance. And we call this energy balance. Okay. Mass balance, the other word is conservation of mass principle. You can see in your textbooks, my notes, you will say this, conservation of mass principle.
Excuse me, sir.
Yeah, Buddha.
Sir, මේ ඔතන මේ දැන් W in Q in වගේ W out Q out වෙන්න ඕනේ නැද්ද? ඇතුළේදී කාර්යයක් කරන නිසා ශක්තිය විදිහට මර තාපේ හානියක් වෙනවනේ.
W in out දෙකම තමයි W in කියලා ගත්තේ net එක. හරි නේද?
ඒ කියන්නේ පද්ධතියම W එක ඔතන තියෙන්නේ.
හරි පද්ධතියම W.
Q එකත් එහෙමයි නේ සර්?
ඔව් මේ තියෙන්නේ මේ ස්ලයිඩ් එකේ ඉක්මනට තියෙනවා. W in net Q in net එක. පස්සේ මේ net කියන එකත් පස්සේ අයින් කරුවා පුතා.
හරි. හරි ඉන් දාපු නිසා පැටල වෙනවා ඒක ඇලිය සර්.
ඒක තමයි. අන්න ඒකයි. එතකොට ඒ කියන්නේ ඩිරෙක්ෂන් එකක් තියෙන්නේ towards නම් අන්න ඒකයි in කියලා ගත්තේ.
හරි හරි.
හරි නේද පුතා? Thank you. Very good.
හරි සර්. හරි සර්.
Very good. එතකොට okay. Conservation of mass principle. The other one we call work and energy balance. We can call it conservation of energy principle. So let me here. The work and energy balance is conservation of energy principle. So I'm looking for some space. Okay, good. Good. Conservation of energy principle. Energy principle. Very good. Okay. So this is the modeling of steady flow open system. Okay. So in the steady operations, we should look at the system. That's why I feel that it is very important to highlight this. I will highlight here itself. Steady operations means system should feel the steadiness. How the system feel the steadiness? By feeling that nothing changes, system feels nothing. The system is there, it has no much impact, no failing. The system feels steady. Steady means no change of energy levels, no change of mass levels. So that is the very important point when it comes to steady, the term steady. Okay, so steady system operation. Okay, so that is very important. Okay, that is very important. Yeah. So you can imagine from here we should start from the system. Huh? This is very nice. So, a steady system operation, that is very important. Other things are very important. Yeah, this looks okay. This looks okay. Duplicate this. What happens? This looks okay. Good. So this is the summary. Okay, this is the summary. So you can see, even you can have this kind of little arrangement in your mind. Open flow systems, it is something like for the working fluid, there is some in and out, energy and work interactions, but system should not feel the change of the energy and the mass levels. That is what we call steady. So no change of energy levels, energy in total, energy in plus work in plus heating minus energy leaving. Of course should be 0 because no energy level rising in the system. System feel good and steady. See the beauty of that. And the mass wise, mass comes in, goes out, but for the system no change. So mass in is mass out. So for a steady system, what steady system means? No rising or changing of energy levels, no rising or changing of mass levels. That is the point, the steady flow system. Okay with that? Yeah. So that is very good. So that is a very good thinking approach. Right? So we are looking within the system. So for us now, steady flow means it is not an equation. So steady flow means M in equals M out, E in plus W in plus Q in equals E out, no such equations. For us, steady flow means no rising of energy levels. No matter for 10 seconds or for 30 seconds or 1 hour, no rising of energy levels and no rising of mass levels. So same energy, same mass. Okay. You understand? I believe you can understand very well. And so this is the point. Now, one more thing. Okay. So you listen very carefully. You listen very carefully, yeah? And you get the important points. Any questions? Please raise. Yeah? That is very good. Now here, previously, at the given time of 10 seconds, 10 seconds. So maybe this starts at maybe 9 o'clock, same like our lecture starts. So starting 10 seconds means 10 seconds past 9. Let's see, this one 30 seconds. Okay, then it's, yeah, let's say 30 minutes. Now, 30 minutes means starting 9. Now 30 minutes past. Now the time is 9:30. Okay, 9 to 9:30. Okay, 9 to 9:30. Lecture time. So here, so this can be 9 to 9:30, or even can be 9:30 to 10, also possible at a given time. Okay, or maybe 9:30 to 10 also possible. Also possible. Or any, starting at any time it is possible, even 12 to 12:30 also okay. That's why. So here, so given time, we can consider it is as a difference in time. See, 9:30 to 10. 10 minus 9:30 is 30 minutes. 9:30 minus 9 is 30 minutes. So time minus time. So this is the time change. Okay, that's why in the time I put both here, T and delta T. Time T and delta T. I put both here because of this reason. Okay, and now for this case, for us, delta T is important. for the steady flow, delta T equals 30 minutes. Yes, delta T equals 30 minutes. Something like that. Okay, delta T equals 30 minutes. Then all delta. See, very nice. Delta T, delta M, delta E. Okay. But delta T is not zero. It takes time. But delta M 0, delta E system 0. It's very nice. So delta T is 10 minutes, or something like that. Okay, for that time period, delta T. So I take, even I can forget 30 and I can take delta T. Okay, I can take delta T. So for 30 minutes, yeah. So like this, so let me duplicate this. And I take everything out and I put delta T. Because now you have familiarity. Delta means difference. That's a notation. Delta means different, means it is increases. Let's say delta means we are taking from 9 to 9:30, not from 9:30 to 9. Always forward. Okay, forward time. Yeah, forward time. Not time from, not time going to past like 9:30 to 9, no, 12 to 11:30, no such thing. 12, then not 11:30, but this is 12:30. 9:32, not 9, but 9 to 9:30. From 9:30, it should be 9:30 to 10. Okay, that's how delta T means. Okay, delta T is that. Okay, understand, Vitana? I hope you can understand. So at a given period time of delta T. Okay, so M in minus M out, like this. So there is amount of mass in. Okay, there is an amount of mass in. So it's like this. So I can write like this as well. Okay, this is a time period. Okay, this is a time period delta T. So as a rate, as a rate, I would write M in minus M out. Okay, per unit second maybe delta T is same as delta M system by delta T. Okay, as a rate. So M in minus M out by delta T. Okay, delta M equals 0 means I will simplify this. M in by delta T, M out by delta T, okay, is 0. Okay, M in by delta T is a rate. So for delta T time period, mass flow in is M in. Okay. So M out by delta T means for delta T period of time, M out. That's the relevance for delta T period of time. M in and M out. That's why as a rate. Okay. So for delta T period of time, see, at a given period of delta T. So this M out is relevant for delta A, delta T. M in is also for delta T. Okay. So M in minus, sorry, M in by delta T. Okay. So you can have it this way. This way. So I can write rate of M in minus rate of M out, okay, is 0. Okay, time rate. Yeah, at a given second maybe as a rate. As a rate. Same way, you can have a rate as well. Okay, so rate of M in equals rate of M out equals 0. Okay. So the other is rate of M in. Therefore, is equal to rate of M out. Very good. Or you can say M in equals M out. That is also okay. So as a rate or as a quantity. Okay. As a rate or as a quantity. So as a rate, this is kilogram per second. As a rate. It's very nice. This is the unit. Generally, we consider rate. Okay, unit is kilogram per second. Here unit is not to say kilogram per second. Kilogram per delta T seconds. See the difference? Yeah. So here the unit is kilogram per delta T seconds. So you should understand the importance of time. Yeah. So rate is more comfortable and more useful. Kilogram per second. This is the initial one. That is also okay for delta T seconds. Good. Same way. Oh, now this goes. Same way. work and energy balance, you can write as a rate raised rate of E in, rate of W in, rate of Q in, minus rate of E out is 0. Okay, as a rate. So here unit is let's say kilojoules per second. Okay, same like in the steam tables and all, you have the kilojoule unit. So I put here kilojoules. Okay. We have 10 minutes. Now we have 10 more minutes. And now I'm going to further simplify this. Steady mass rate of M in equals rate of M out. Okay. And let's say this is M dot. Okay, very nice notation. Okay, M dot kilogram per second. So rate normally we can use as M dot. Okay, rate of E in. Okay, rate of E in. So you can use this as rate of E in. Let me write E dot. Okay, E dot. So E dot in. Okay, interesting. Is E dot out. Even for Q, you can write Q dot in. Okay, W dot in. Equals 0. Okay, so dot means it's a rate. Okay, dot. So M dot means this is mass rate. M is mass, dot means rate. Okay, so this can be the mass rate. So here it's a flow rate. Okay, mass rate, M dot. So it's very nice notation. Don't worry about this. So if you think of E dot, E dot again, something like energy rate. Okay, for sure. And when it comes to W dot, W dot, so this is something like work rate or power. Power, W dot. Okay, work rate or power. Okay, so mass energy rate is kilojoules per second. Okay, work rate also kilojoules per second. So this is quite interesting, quite interesting. Right. But some cases, instead of W, people tends to use normal W as well for work rates. Sometimes for W dot, people are using W as well. Yeah, sometimes, so don't worry, sometimes use W as it is. It is for W dot. So don't worry about that. Okay. For some cases, we can notice this. Some cases instead of W dot, they are using W. That is also okay. Yeah, because don't get confused on that. Huh? So this is another summary. And, W is here, U plus W. I hope you have some understanding. Okay. And if you have time, let's see if we take one more here. Some more interpretations can be in this way. Rate of En, rate of W, this is fine. Sometimes you can see En. If this is okay, you can write this way as well. By M dot. E out by M dot. Okay. M dot. So kg per kilojoule per kilogram per second. Now, this is the unit now. So this can be written as instead of big E, you are using small e. Okay. Big W, small w. Big Q, small q. Okay. And then no M dot is here. So here, instead of big E, small e out. Is there. Kilojoule per kilogram per second. Okay. So that is another interpretation. Okay. Quite nice. This way. So it is nothing but simple manipulation of the notations. E dot simple means we know it is for 1 kilogram of mass flow. 1 kilogram per second mass flow. Right. Okay, don't worry. Next week we will try to drill this one some more. So today even you can look into your textbooks, notes, and it's mentioned all the things in different but easier ways. So next Friday we will do some more analysis on this. This is not the final form. because next week we should understand, for the next week, we should understand these things. What E means. E. How to write E. Understanding this. Okay. Understanding E and E dot. We have to understand this. Now, so given understanding the big E's. Yeah. So to understand this. Dot. Also understanding this one. Okay, these are the two important things. So, understanding this. Yes. So this will be next week discussion. So after that we are ready for even to do exam questions. Okay, don't worry about that. This one. So today, if you look into the summary, now only 43 here, some left. If you look into the summary, this is the starting flow work and energy model with some case studies here. This is a pump, then the pump. The model again, we recognize the surrounding system boundary and the system, and the flow in, flow out, work in, and heat in. Work in means net work, heat in means net heat. Okay. Here also it's the same. Open system, flow in, flow out, work in, and also we consider heat in. Heat in and heat out both we consider heat in minus out, just put here. It's example 10 watt in, 2 watt out means a total 8 watt in. That is heat in. Okay. In another example, the refrigerant compressors, we see the same in and out. And the word steady flow introduced. Then for steady flows, this is the turbine system, steam turbine system. So then steady flow means what? That is the thing we introduce. Steady flow, we consider flow balance. Okay, Buddha. Okay, yes. Sanjeev sent the message. Okay, so consider flow balance as the steady flow. Then boilers. Okay, we introduce. And the flow system, if no in and out, it is like not live. Okay, so no mass flowing, mass flow balance is there, but that is not live system when it comes to steady flow or the flow systems. Okay, the live and continuous or steady operations. So here flow balance, we wrote equations, work energy balance, we use the keywords here, just put the keywords on and slowly 10 seconds we wrote the expressions. Okay, and then some more. About this energy balance and the mass balance, and further continuation of this. And then we have introduced what steady operation means. Delta E system 0, delta N system 0. And the steady flow means this really. The relevance is for the system. Okay. So steady operations, steady systems. So steady flow system. Yeah, very nicely introduced. The equations are here. E in, W in, Q in minus E out. 0. Net in minus net out. For M in equals M out. Mass balance for 10 seconds. So then we came to know the concept of delta T. So 10 seconds or 30 minutes, so delta T we have. And then same expressions for given time delta T as per kg per second or per kg. So M in equals M out, kilogram per delta T seconds. Rate of M in, rate of E in, rate of W in, the rates introduced. Then rate of M we introduce as M dot. Rate of energy we introduce E dot. Work W dot, but W also okay, we can just use W as well. Q dot, okay. Actually heat normally supplied as a rate. Later we will see, okay, don't worry. Expressions with dot, okay. E dot in plus W dot in plus Q dot in minus E dot out equals E dot. We call this E dot. W dot, Q dot. Generally, we refer this dot term to rate. If there are double dots, two dots, we call it acceleration. Okay, rate means the double of time. Yeah, it's a rate of rate is double dot. Yeah, good. So next week we will look into this. Okay, understanding E dot 10. Simple E dot the rates, and we will be ready for the exam questions after. Yeah. So not like teaching face to face in the classroom. Teaching in this way is a little tough unless you raise some questions. But someone raised questions, very good. And one student asked about the Tesla. Are you still there? Tesla vehicle or Tesla battery? Someone asked a question. Okay, so maybe you can email me or you can ask it. So now I'm going to stop the class. Yes, don't worry, I will mark the attendance. Don't worry, I will mark the attendance. Very good. Yeah. Okay. Good, Putana, that's all. So see you next Friday. You can feedback on the lessons, How do you feel? You feel good or bad? How is it? You can discuss these things. And also last Friday discussion, I asked you to explore something. Yeah? I shared some nice, say, interest with you to do at home. Yeah. So try to do something extra other than this reading of the books and the notes. Yeah. Okay, Bhutala, so let me stop the class now. Bye then. Bye.
Thank you, sir.
Okay, Bhutala. Bye. Bye.
Thank you, sir.
Bye, Bhutala. Thank you very much. Okay.